So let's talk about the architecture details. So I talked about the overview. I talked about the components, and then now let's talk about the architecture of this. What we're doing in here is we're actually doing we're providing for predictable performance, and the way we do that is by doing a crossbar-based fabric. So what that means is that you have 384 ports that are that basically the traffic can go out on. And we have a crossbar-based fabric in the middle, and we have queues on each ingress line card for each of those destination ports. So let's say if one of the ports is backed up, then the other ports are not affected because they are separate queues for each of the ports. And we have a central arbiter acting like an orchestra master, which so when packets come into these queues, so 384 queues per line card, when a packet comes in, it sends a request to a central arbiter and says, hey, listen, I want to send to that destination over there. And then the central arbiter decides, okay, it's your turn to go, or it is his turn to go, and so on. So that central arbitration provides for a predictable performance. Now we also support 4 qualities of service. So you have these 384 queues, and you have 4 qualities of service per queue, so that way you can pick and choose between those qualities of service. And then for each of those queues, we actually have queues on a per input line ports perspective to allow for fairness. So that, let's say you have small packets and large packets. So by having queues on a per ingress port perspective, what that allows you to do is you pick and choose, you basically can do a round robin between these different queues. So let's say, it's not like one queue has, one port is bringing in large packets and another port is bringing in small packets, and then you're just sort of like picking the large, picking the small, picking the large, and so on. And that's, you would not give proper fairness to it. So we provide for fairness in between these packets by going through these queues into the chassis. So multiple queues in the architecture. So the key thing here really is we have virtual output queues. So what we call is this virtual output queues, where there are queues on a per destination basis with a central arbiter and quality of service per one of those virtual output queues.
So will this also address slow drain issues?
I have a slide on slow drain.
Sorry.
So the packet flow, I'm not sure you can read this. The font is very small. I apologize for that. Didn't realize it. So what we do, this is just sort of like a day in the life of a packet, right? And these are the blocks on the line card. And what you're seeing here is this is the line card, which has these different logical elements on it. The packet comes in. Error checking is done on the packet right at the very input. And if the packet is bad, we drop the packet right there. We look at, so we support virtual SANs on a per port basis. The packet comes in, we look at the vSAN on it, the quality of service, and we timestamp the ingress frame coming in. Then we take it to the forwarding, and we do access controls. Where is this packet allowed to connect to? Zoning, load balancing. So if you have, let's say, port channels that is the final destination. So we'll do load balancing across them, inter vSAN routing, and then the virtual output queues that I talked about. So there are these queues, lots of queues that we're arbitrating across, and we're maintaining these virtual output queues and doing frame buffering in these queues and doing the arbitration across them based on quality of service, based on the destination that they're supposed to go to. And the reason this is important, these virtual output queues are important, is that as opposed to, let's say, an architecture where you have a switch on a chip ASIC, and you replicate the switch on a chip ASIC multiple times, and then you actually don't have a central intelligence. We have a central intelligence in the architecture, which allows you to sort of switch packets between the different line cards. You're smiling, Chris. Okay, good. And then this is showing that there's a centralized arbiter with a crossbar fabric, and then on the egress side, we're again doing some egress access controls depending on whether these packets are allowed to go to a destination or not. And then also checking the CRC as well again, because the packet may have gotten bad when it went through the switch. So before you finally send the packet out, you again check the CRC. And then you basically send the packet out. Any comments? Questions?
In the future, that is pretty much, I can't read that. So.
Yep, sorry about that.
I don't know if it was,
yeah, I think it's, I think we have white papers and stuff that we'll be writing on it as well, so there'll be more details. There's just too much detail in too small a slide. Yeah, great. Okay. So looking at it from a frame flow perspective, how do the frames flow in this chassis is, so when a packet comes in, so what this is showing is basically we have I/O slice ASICs on the ingress, and this is a 48 ports, so 8 ports per each of these ASICs, and 6 of these ASICs with, when a packet comes in, it makes an arbiter request because it gets queued up in a virtual output queue, and once the arbiter says, yep, you can go to that destination, or maybe that destination is congested and it just doesn't service that port. It grants this packet permission to go across the fabric and across the backplane. So what this really means is that if there are any outputs that are congested, they're not using up fabric bandwidth. And they are just sitting in their queues, in their special queue, in their queues for those ports, destination ports. So once the permission is granted, the packet goes from the I/O slice to the crossbar on the line card, goes to the fabric, and then it can get routed to any destination port, and then it comes out on the egress side to the egress I/O slice ASIC. And then basically the packet is sent out. Now, talking about slow drain, so just to build up for slow drain, before I talk about slow drain, I wanted to talk about B2B credits. And what this is showing is basically fiber channel flow in a network where you have a sequence initiator, you have a fabric, and you have a sequence recipient. And you've basically got packets going from, let's say, a TX buffer to an RX buffer, and then so the way this process works is when a device comes up, it negotiates with the other port that it's talking to in terms of the number of buffers. So let's say if I'm an initiator and I'm going to send him packets and I come up, so I talk to the switch and say, well, how many buffer credits do you have? He tells me how many buffer credits he has. I tell him how many buffer credits I have, and basically then we can share packets. So I can, if he says he has 10 buffer credits, I can send him 10 packets, and then I won't send any more packets. And then he has to return the R-readies back before I can send any more packets. So that's how the flow control works in fiber channel. And this is basically what this is showing, is that packets are going from the sequence initiator to the fabric, and then to the recipient, and then R-readies coming back. And same thing, so let's say an ACK coming back, and same thing's happening because ACK is a packet as well. Okay? Any comments? So this is an example of what I just mentioned. So you've got packets going from a source to a destination. And you've got, in this example, 8 packets going. And when a packet goes, you send an R-ready back to the source. Right? So this is basically buffer credits and packets being sent, R-readies being sent back. And that's how the flow control is happening. Now, what happens is that in large networks, we hear from customers is that they may have a misbehaving device. For example, they may have an old HBA in this network, or they may have the firmware on the HBA is old, and maybe they have a bad SFP or cable or something to that effect, and it can be transient in nature. So which is really the odd thing. It's like during the day, it happens some times of the day, but doesn't happen all the time, right? And so it becomes kind of hard because your applications slow down, you try to figure it out, but the condition has sort of moved on. And that's really what's happening, is that a receiver is not returning B2B credits fast enough. So like, let's say like an HBA with a bad firmware or something like that, maybe most of the time it's okay, and then sometimes it stops or slows down returning B2B credits. So this is showing an example where, let's say, a source came in and did a read from a storage array, right? And then there's data coming back from the storage array. And maybe the HBA and the speed on the device, on the HBA is kind of low, and the storage array is an 8 gig storage array, so it's basically just blasting the data back. And then you're sort of seeing this happen. So it's slow in returning B2B credits, so this packet sort of build up in that queue that's facing that device. Now, what that means is that across the crossbar on the ingress side, maybe a packet builds up in one of those queues. And then because the ISL or the interswitch link is carrying packets for multiple destinations through that interswitch link, the switch that it's coming from, the green and the blue, are now sort of starting to back up because this green is sort of head of line blocking the blue. And then you basically are starting to see slowness in your network. So what we do is, first step for customers is, when somebody reports that your network is down, how do you sort of go about diagnosing that? We're providing for locating slow drain conditions. So there are multiple counters that can be monitored in the network to see where is this slow drain happening in your network. So that's the first step, to diagnose and figure out where the slow drain is. We also have, what we're also doing is, with the 9710, we're providing for hardware-based counters for slow drain. So, customers, it basically provides you instantaneous results of, let's say how many packets are queued up and so on. So that's something that, we're working toward. So the capability is there, and we're, going to be bringing it out in an NXOS release.
Will that be something you can see with the setting of a flow of DCNM?
So so first step is CLI, and then there's the DCNM piece.
Okay.
So, DCNM piece is a roadmap item. Obviously, it's of big interest to us that it be in DCNM as well, but it's a roadmap item. Now, what we also do is we provide customers the capability to recover from slow drain. And one tool, so one thing is, when packets have been in the network for more than 500 milliseconds, fiber channel, as per standard, the packets get aged out. We also provide the capability that on a per port basis, that you can set a timer, what we say the no credit drop timeout value. So let's say if a packet has been, if no buffer credits have been returned for 200 milliseconds or 300 milliseconds, you can start dropping packets in that queue. So basically, if you could start dropping packets right here, if this thing is not getting its B2B credits back, then you're basically not congesting up the rest of the network. So we provide for that capability where you can go ahead and set this no credit drop timeout value on a per interface, for the switch, for an F port or an E port. Okay. We also, provide the capability to recover lost credits, so the link can be reset and can be flapped, and then that negotiation can happen again for getting the credits back. And if this thing is just not working out, you can error disable the port. So these are the multiple capabilities that we have in the system for addressing slow drain.
So except for the hardware counters, this is also possible in the 9500s, right?
That's right. Yeah. So again, with 9710, it's the next generation, so we're sort of taking it to the next level. But good point on the 9500.
But on the next OS level, you'll support the hardware counters.
Right, so we're working towards that.
Yeah, but that OS level will not be able to record counters on the older MDS series then for
No,
detecting
it'll be
flow drain.
different. It's different platforms. So the
Yeah.
same OS will work the same way for the 9500, and then it'll just handle those
It'll
things.
just lack features. in
Because
the
we
older
know
systems.
which platform we're working on, right?
Yeah. Okay.
So.